understanding of the flow a script follows when executing will be very beneficial for shell scripting, as it can help you be more efficient, save time debugging, among other things. Complex software is different and more difficult to analyze as it provides many points of entry depending on which component of the UI was clicked, for example, as this would execute a different functionality that changes the execution order. Gladly, shell scripts are generally very linear and easier to understand, analyze, and debug, as they provide a starting point that begins from the top of the executed script, running each command from top to bottom. However, the order of command execution in shell scripting can be changed by using control structures such as loops, conditional statements, or functions. These allow you to execute commands based on certain conditions or to execute the same command multiple times with different outcomes. A basic example of a conditional statement in real life can be going to the movies. If you have ticket to the movies, you are allowed inside the theater. Otherwise, you're not. This is called a branching of possibilities that might occur depending on the conditions. Now, to advance in your shell scripting skills, being able to create complex workflows that depend on each other to continue with the automation chain of command is very important. A closer analogy outside of programming, which illustrates a well-crafted script that considers this complex workflows, is a factory analogy. Imagine that you are running a factory that produces widgets or anything really that requires multiple steps that serve as a precondition to be met before the next step can be started. Each product must go through several stations in the factory to be completed. In the first station, for example, the widget is inspected to make sure it meets certain quality standards. If the widget passes the inspection, it moves to the next station. If it fails the inspection, it is set aside for repairs or scraped. In this scenario, the inspection station is like a control statement in programming. It determines whether or not the widget, which is like a piece of data in a program, meets a certain criteria. And based on that evaluation, it either allows the widget to move on to the next station, which is like executing a block of code, or moves it aside for repairs, which is like skipping a block of code. Okay, so we are just defining that control statements allow a program to make decisions based on certain conditions. But what I want you to get from here is that there are certain techniques that can be used specific to a coding language. And in this course, I want to teach some of those techniques for shell scripting that will help create reliable and flexible scripts that can respond to different inputs and conditions in appropriate ways. There are four main programming constructs that can alter the imperative programming flow in shell scripting. I'm talking about conditional statements, loops, sourcing code from other files mid-script, and using functions. Let's have a quick crash course refresher on these topics, starting with if statements and looping syntax in shell scripting. If any of these concepts seem too unfamiliar, head over to the Shell Scripts for Beginners course to learn the basics. Here, we have an if function that will never evaluate to true because 3 will never be greater than 4. This sample is just to illustrate that there are blocks of code that don't necessarily always run. And by the way, you might encounter different syntax styles for if statements in shell scripting when reading other people's code. In this course, we will use double square brackets over single square brackets to wrap the conditions, as double square brackets allow a wider range of condition evaluation style than the single square brackets. We will dive deeper into that topic in the built-in command section. Here, we have another conditional control structure using the case keyword. We learned the case keyword in the Shell Scripts for Beginners course, but to give a quick refresher here, this code illustrates how case keyword is evaluating a variable word that can have any value really. In the sample, we want to perform different actions if the value is matched by any of the pattern 1, pattern 2, or 3 options, meaning that if word's value contains a match for those values, it will enter the code defined between the pattern definition, executing whatever statements or commands we have in between. We have an extensive lecture dedicated to the use of case for building robust command line scripts in a future section. Another common control flow statements in programming is looping. Creating loops is a control flow statement that changes the regular execution order in a script. This type of blocks allow a program to repeat code a predefined number of times or until a certain condition is met. We have the for loop, while loop, and the until loop. As you can see on the screen, there are many different ways in looping syntaxes in Bash. To illustrate my point, we have 6 different syntaxes we'll show you that more or less achieve the same result. On the right side, we have a for loop with an incrementing counter variable. This will print iteration 1, iteration 2, and iteration 3 on the screen when executed. On the left side, we have a while loop with an incrementing counter variable. This also prints iteration 1, iteration 2, and iteration 3. The differences between these two are the techniques used to exit the loop to avoid being trapped infinitely in there. While loops generally use counter variables to have a condition evaluate to false at a given point to provide a means to end the loop. For loops generally have a predefined number of times for their execution. In this sample, we see another syntax for using the for loop. In this case, we're using the seek command, which is used to print a sequence of numbers. The command is wrapped in a command expansion subshell, which helps shell treat the output of a command as if it was a variable being read. On the left side, we have an until loop with an decrementing counter variable. These two loops produce the same exact output as the other two samples as well. In this case, the until loop runs until a condition is met, so we use a similar counter variable that will keep track of the number of times we've iterated in that loop to provide a control value to help exit out of the loop when a condition is met. Now, we have a couple more techniques used for creating loops using while. We have a while loop with a range of numbers generated using seek and read, and a while loop reading from a file called fds.txt that treats each line as an iteration element. Now, I want you to see the following pattern to make looping syntax and shell way easier. Two things present in all of these different loops are a do keyword, which appears right before the block of code that we intend to execute multiple times based on a statement, and the done keyword, which indicates that anything that comes after done is out of the looping block. For now, we will not dive deep into these concepts other than seeing the syntax presented in these examples. Just keep in mind the following rules of thumb. For is generally the better choice when we know exactly how many number of times we want to repeat the loop. While and until are the better choice when we want to loop until a condition is met, but we don't know how many number of times that could take. While is better for reading files and repeat a loop over file elements. Now, when running a shell script, we can call another script or source file written in a separated file using the source built-in command or a single dot, which is also a shell built-in. To use this technique, we type dot or source followed by the name of the script or file to be called. This will execute the commands in the sourced file as if they were part of the original script. As you can see, on the script sample on the right, there is no variable name declared, but on the left, we are showing a command snippet that assumes a conf file is present, and this file has a variable declaration name inside. When executing conf read v1 script, what's happening is that we are sourcing the conf file in the second line of the script. On the third line, we attempt to echo the value of name. In this sample, we illustrate how this executes successfully, printing the value of name to the terminal. A more appropriate implementation of the previous example would be to use an if statement to verify if the conf file exists before sourcing it. To understand this code, let's keep in mind that shell scripting with Bash allows if statements to evaluate conditions to true or false inside double square brackets. What's important from this sample is to read and analyze how we are now creating multiple branches from a basic script flow by using techniques like sourcing files and using conditional statements, but also the reasoning behind teaching this right now. As we've been talking about how scripts should only continue when pre-made conditions are met, we are pairing this idea of writing scripts in this way with the analogy of a factory producing widgets, where we only want to move to the next phase of the widget production process if the previous conditions were successfully met. In this sample, we see how in doing cat to a conf file, we get a no such file or directory, which illustrates the absence of the conf file in our current directory. On the right side, I'm illustrating a strategy to evaluate if a file is present. The syntax -f evaluates a value as true if the string's value is a file that's present. In this case, we're expanding the conf file constant as the expression to evaluate. I'm doing this because good shell scripting involves anticipating to the fact that a file might be absent when we run a script, so we want to create alternatives to keep the execution going if possible. The purpose of this script is just to echo a name. So if the file is absent, which means the square bracket condition will evaluate to false, we will initialize the name variable inside the script. Then we will expand the variable with echo to print it to the terminal, as the second command illustrates. We will learn more about the use of square brackets for conditional syntax in the following lectures. This is an illustration of the more appropriate implementation of the script we saw in the previous example, which illustrates how the script would behave if the conf file is present. As you can see in the sample, the script now prints Juan Carlos to the terminal when executed, and this is because we are assuming the conf file is present this time, so we are executing the source command inside the if statement. We will see functions as another way to control the imperative style flow in our shell scripts in the upcoming lectures, but first, we will revisit some topics to make sense of some of the concepts we will explore when learning functions. I want to encourage the use of functions as much as possible when doing shell scripting. In the previous lectures, we went over how scripts written in Bash follow an imperative programming style for the most part, and how the commands written from top to bottom generally execute in that order. We also went over 4 main scenarios when scripts don't execute from top to bottom. These techniques can be used to control the flow of our scripts. I'm talking about conditional statements, loops, calling or sourcing code from another file, and functions. In this lecture, I want to talk about functions and why they're an important topic to master, mainly because functions encapsulate blocks of code that can be called repetitively without having to rewrite them repeatedly. To think about how functions work with a real-world analogy, imagine that you're a chef at a restaurant and you're responsible for preparing several dishes, such as salads, sandwiches, and pizzas. Each of these dishes has a specific set of steps that must be followed in order for them to be prepared correctly. Following this analogy, the first time you prepare a dish, it's okay to take extra attention to detail, as you're meticulously designing the most efficient steps to prepare the dish. In the long run, however, carefully following the same steps over and over can become really time-consuming and error-prone. If a chef could capture the steps that were carefully followed for a dish and abstract them into an implementation, that would allow those steps to be reused in the same order each time, with all the ingredient considerations, measurements, etc. This would make your life at work a lot easier, and gladly, when coding scripts, the use of functions can help you reuse a series of steps we've carefully put together by thinking about all possible scenarios. We just need to encapsulate those steps into a function bracket and call them each time. This way, you wouldn't need to remember or look up all of the steps every time, and moreover, you wouldn't have a chance of making a mistake, because the function is already hard-coded and it's just like pushing the replay button every time. A good function is written when you can also input values to make a generic set of steps more concrete to a given scenario without breaking the existing functionality. In the chef analogy, this would be like having the ability to run a function to make a dish while excluding certain ingredients. This would be similar to performing certain actions like creating a backup, for example, where we want to pass as an argument which file to perform the backup against. This sample code illustrates my point exactly. Writing scripts that handles backup files is probably one of the most common tasks we do as DevOps. However, thinking about all the scenarios that we want to consider is generally just a one-fit solution that works for a specific use case. Here, we are creating a backup directory, and then we are copying a file named file.txt into it. Then we use a tar command to compress the file into a file named backup.tar.gz, and then we exit our script. Without taking much into this implementation, imagine that you find the perfect order to pile up your commands to help you create the backups for your specific directory structure and your unique situation. But then, every time you need to make a backup, you have to write those sequential steps in the same order over and over across your script. You'll end up having a hard time maintaining your code this way. A better approach is to use functions, as they allow to group together a set of instructions that can be executed repeatedly. So once you have perfected the steps that help you resolve a particular task, you can group them together in a function. This way you can just call them each time they're required, as they can be reused while your script grows larger and more complex. Functions make your code more organized, efficient, and easier to understand. Let's use the previous example of cloning a Git project with command line arguments and improve it further to include the use of functions. We could go from here to here. In the second example, we can see how the script begins by setting a variable git_URL to the value of the first command line argument. This argument should be the URL of a Git repository that you want to clone. The script then defines two functions, git clone and find files. The git clone function takes a single argument, which should be the URL of a Git repository. The function will use this argument on the git clone command to clone the repository. The find files function uses the find and wc commands to count the number of files in the current directory. Finally, the script calls the git clone function with git_URL as its argument, which will clone the Git repository specified by git_URL. The script then calls the find files function, which will count the number of files in the current directory. All right, so now that we've talked about benefits of using functions and we've seen samples of how functions can be implemented to improve our scripts, let's talk about function declaration syntax. In Bash, there are two main ways in which we can declare a function. The most common way, and the way you'll see it being used in this course, is in the way it is defined on the left-hand side. Another way to declare a function is by using the reserved word function. As you can see, the example on the right lacks parentheses on the function declaration block. However, the parentheses can still be used along with this syntax, but they're just optional. These two function declaration syntax can be used with one-liners as well. This means just typing them directly in your terminal, and you should be able to see an output similar to the one shown in the screen. As you can see, invoking a function from the command line requires just typing the function name after it's being declared. These two samples produce the same output, but as defined earlier, we will generally prefer the function syntax declaration with parentheses and avoid using the function keyword. This is for style and portability with previous versions of Shell. Let's now talk about declaring local variables inside a function. Most coding languages follow similar principles of variable scope. The local keyword is used to declare a local variable. When a variable is declared as local, its scope is limited to the function. This means that the variable cannot be accessed or modified outside of the function or script where it was declared. Variable scope is a foundational concept studying programming and software development. But understanding that local is a modifier that prevents a variable's value from being accessed from outside of a function where it was declared sufficient for shell scripting purposes. As you can see in this example, trying to echo the value of var1, which is declared as local inside the function, produces an empty output, as the scope of the variable is limited to the function. Here's a corrected version of this script, where echo var1 is called from inside the function. In this version, we get a hello output, as we are making a correct use of the variable scope by attempting to access it from the correct place inside the function. There are several advantages to using functions in programming: to organize and reuse code, to make code easier to read and understand, and to divide a large program into smaller, more manageable parts. This is one of the most important topics when learning shell scripting, as it's one of the main ways, and the first one we are seeing in this course, I think, on which we as humans can interact with a script. So far, we've seen examples of scripts coded perform automated tasks without much regard of user input or customization based on different needs. Command line arguments are a way in which we can interact with the same code being executed with different inputs without having to change configurations on our systems directly or make changes to the code itself. For example, I see the use of command line arguments very close to using a remote control to change the channels on the TV. The remote control is like an interface to a lot of different functionalities we can perform by pressing different buttons. the same way as we can pass different command line arguments to a script to make it behave differently. For instance, when you want to change the channel, you press a button on the remote, for example, channel up or channel down. You don't have to have two different remote controls for each different thing that you want to change on your TV watching experience. Instead, you have a remote control that can exhibit different functionalities depending on the arguments you provide. This is similar to providing command line arguments to a shell script. The remote control receives the input, which is like the command line argument, and takes the appropriate action, in this case, changing the channel. Just like a shell script, the remote control needs specific instructions in order to perform the actions that you want it to. Alright, so let's assume you were tasked with writing a script that clones a Git project. The script should also find how many files the project contains. We could use a sample script being shown on the screen. This script is running a git clone command to clone a Git repository. Then, it uses a find command to search for files in the current directory and its subdirectories. The -type f option tells find to only look for files and not directories. The find command results are then piped to the wc-l command, which counts the number of lines in the input, giving us the total number of files found. While this script works, having it written in this fashion would mean that each time you want to use it to help you count the number of files contained in a repository, you would need to go and edit the script, delete the third line, and add the URL for the project you want to count the files for in a hard-coded fashion. By the way, the Git URLs shown on the screen don't exist in case you're about to try them out. This is an inefficient process as this requires a lot of manual intervention, leaving little room for automation and portability. These issues can be fixed using command line arguments. This script runs a git clone command to clone a Git repository specified as the first command line argument. The $symbol and 1 syntax is used to pass the first command line argument to the git clone command. So as you can see, command line arguments allows us to pass information to a shell script at runtime. This can be useful for customizing the behavior of a script or for passing data that the script needs to process. Command line arguments are additional pieces of information that are passed to a shell script when it's invoked. The command line arguments are typically separated by spaces and are added after the name of the script. This is a sample script that illustrates how each word separated by a space we type after invoking the script is treated as a command line argument. As you can see from this sample, command line arguments have a positional parameter based on the order in which they're passed to the script. Their value can be expanded in a shell script with a $symbol, followed by the positional parameter of the argument, starting with 1, all the way to the number of arguments being passed. For example, here, the arg3, which is passed at the utmost right position, can be expanded by its positional parameter $3. In case you're wondering, the maximum number of command line arguments you can pass to a shell script in Unix-like operating system is typically limited by the arg_max constant. In this example, I'm showing how to check the value of this constant using getconf command. This value should be roughly about 1 megabyte, which for command line arguments, similar to arg1, arg2, and arg3, I think should represent about 100,000 arguments. Okay, so to close this lecture, let's explore the use of the shift command. The shift command can be used to move the arguments down one position like this. In this example, we are printing 3 times the argument 1, but if we examine the output, the 3 positional parameters are being printed on the screen. This shift command is very useful for creating a full command line interface script. We will explore more of these functionalities along with some parsing techniques in later sections. That's it for command line arguments. See you in the lab exercises. Think about it, a shell script is a collection of commands added in a file on which we use several programming constructs to automate complex tasks. From what we've learned about process IDs in previous courses, we know that when a new process is created, the kernel assigns a unique ID number that can be used to track and manage the process. So, have you wondered how many process IDs get created during the execution of a shell script? To explore these mechanics, let's use the same chef analogy we've used in previous lectures. This time, we're going to imagine that the chef is similar to a parent shell and the workers helping him in the kitchen are process IDs invoked by commands running in the parent shell. In shell scripting, a parent shell is the shell that launches when we start a new terminal session. The parent shell has a process ID similar to any other process. Within that terminal session, we can type and execute commands. This will generate additional process IDs, and these IDs will be called child processes and they will be associated with the parent shell. In this analogy, each instruction given by the chef occupies a resource, which is one of the workers or kitchen employees completing a task. The chef assigns each person a unique identifier, just like how each process has a unique ID number. The chef can view the status of each person's task, just like how you can view the status of each process using commands in the terminal. The chef can also stop or restart tasks if needed, just like how you can stop or restart processes using the command line. So in this analogy, processes invoked by the shell are like a team of people working in a restaurant kitchen. Each person is like a process, and they have a specific role to play. This illustration shows a relationship between a shell and the terminal. The terminal session running a shell process is associated with a TTY. A TTY, short for teletypewriter, is a device that allows users to interact with the system through a terminal interface. In Linux, each TTY is associated with a unique process known as a session leader or parent shell. The session leader process is responsible for managing the TTY and the associated terminal interface. While a TTY is associated with a single session leader process, it is possible for that process to spawn child processes that are also associated with the TTY. These child processes can have their own unique PIDs, but they remain part of the same TTY session as the session leader process. We already talked about TTYs in the interactive versus non-interactive shell lecture in this course. For the purpose of understanding process IDs and their relationship with the shell, let's keep in mind that a TTY is an identifier that helps link or relate a shell parent process with a terminal session. Therefore, each tab you have open in your terminal will have a TTY name associated to it. To find out the TTY name associated with your terminal, type the command TTY as seen on the screen. So now that we're understanding the theory behind the shell sessions in the terminal, let's analyze what happens when we invoke a script from the terminal. When we invoke a shell script, a child process is spawned. Any child processes that are spawned by the shell, such as background jobs or sub-processes, are also associated with the same TTY, but they have their own unique PIDs. To see the process IDs associated with a specific process, I generally use the ps-ef command along with a grep command to match a name of the process I'm looking. There's a whole section about grep later in this course. For now, keep in mind that grep is a command line tool for searching text. I'll dive a little deeper into managing processes at the end of this lecture as well. Here, I'm sharing my terminal, and I'm going to check the TTY associated to this tab. For this, I'm typing the TTY command. Observe how now I will use ps-ef grep bash to check the bash process is running on my system. This value on the left is the process ID for my bash session. Now, I'm going to open a second tab, and I'll repeat the process. Observe how now a second bash process appears when I do the ps-ef grep bash. Each bash process is associated to a different TTY. Now I'm going back to the first tab, and I'll create a script named script.sh. The script will just contain a sleep command to make the script hang in there for 180 seconds while we examine the process IDs. If I run this script, however, the terminal session gets locked as the script is running a sleep command that will take 180 seconds to complete, rendering my terminal unable to receive any commands for the duration of the sleep command. Let's go to the second tab really quickly to see what's going on. If I do ps-ef and look for bash, I see that the script.sh is running. Observe how the script has its own unique process ID. Next to its process ID, we see the process ID of the parent shell. Observe how this PID is the same as the one from the bash parent shell session running on the other tab, as observed by the relationship between the TTY, the PID, and the process name. Now, I'm going to do a ps-ef to the sleep command, which is running inside the script.sh. We see that sleep is a command that is generating a process ID on its own, and we can observe the same relationship between the sleep command and its parent process, which is the script.sh script we used to invoke the sleep command. We can trace this back to the parent shell, so you can now get an idea about the relationship between each one. The TTY is associated to a bash process running in a tab. The bash process has other child processes running, and each child process can have other child processes running on its own. Now, before closing this quick demo, I want to showcase a couple of techniques to manage processes and the way they're associated to a session. I'm going to do Ctrl+C on the script.sh running on our first tab to terminate the scripts. Now, I'm going to run the script again, passing an ampersand symbol next to the script name. Observe how this time the script is being sent to the background so I can use my terminal freely to do other commands while the script is still running. There is one problem though, the script is still associated to this terminal session as seen on the relationship between the process ID and the parent shell, which points to the bash process running in the TTY associated with my terminal tab. If I close this tab, the process dies as I'm going to show on the other tab I still have open. To detach a process from a TTY, we can use the nohop command as I'm going to demonstrate soon. By running the script with nohop and ampersand, I'm sending the script to the background, and I see how by running ps-ef, the script seems to be associated with the TTY from this session as normal. After validating that the script is running, I'm going to close this tab and check on the other one to see how the script is still running. After closing the tab, I'll check ps-ef grep script.sh to observe how the script has been disassociated from a TTY. This is in essence the difference between nohop and ampersand. With the ampersand symbol, we send a running process to the background. A process will continue to run even when the terminal where it was executed is closed, as we disassociate a process from a TTY. So far we're getting that running scripts generate a process ID and the commands executed inside the script generate a child process ID associated with the scripts. However, not all processes generate process IDs. There are some commands that come already pre-packaged in the shell called built-in commands, and these don't generate a process ID when invoked in a traditional way. Some built-in commands can be found as binaries, and when executed by referencing their absolute path, they will generate a process ID. In the next lecture, we're going to learn more about these mechanics and the benefits it provides. I want to talk about process management in Linux to close this lecture. A very in-depth explanation is out of the scope of this course, as the topic can be explored very extensively, so let's have a quick crash course. For running processes, we have that. You can simply type the name of the program and hit enter or add it on a script, just like you do with commands like ls, cat or echo. Programs can be run using their absolute path, like the usr bin cat shown in the screen, or from anywhere in your file system just by typing their name as long as they're added in the path environment variable. The // notation we use to run scripts indicates that we're using a relative directory as indicated by the dot, which means current directory. For listing processes, we have that. You can view a list of all running processes on the system using various tools, such as the ps command or the top command. For this course, we will use ps command along with the ef flag to list processes. The ps command stands for process status. The flag -e passed to the ps command specify that it should display information about all running processes. The f flag we pass in conjunction with the e flag is to include detailed information about each process. To terminate a process, use the kill command followed by the process ID that should be terminated. Kill command sends a signal to the process requesting to perform a certain action, such as terminating gracefully or terminating forcibly. The default behavior of kill is sigterm, which requests the process to terminate gracefully. For example, to send the sigterm signal to a process with process ID 99838, you can use either of the following commands listed on the right. -sigterm, -15 or -term mean the same thing. If the process does not exit within a certain time limit, you may need to send a sigkill signal to forcibly terminate it. For example, to send a sigkill signal to a process with PID 99838, you can use either of the commands seen on the right side of the screen interchangeably, like -9, -kill or -sigkill, followed by the process ID number. And lastly, we have that for tracing, we have strace, which is a command line utility used in Linux to trace and debug system calls made by a running process, showing detailed information about each call. Strace can be used to analyze system calls associated with commands and processes. During this course, we will use strace in the following way. Strace -TFP followed by a process ID for our parent shell. The -T option passed to strace is used to display timing information for each system call. The -F option to strace is used to trace child processes as well as the parent process. The -P option to strace specifies the process ID of the process to trace, in this case the parent shell. In ID's lecture, we learned that the commands contained in a shell script will generate multiple process IDs when executed. Generating process IDs is time and resource consuming, and resources are usually limited, so can a very large shell script consume a large amount of resources?
Gladly, shell scripts are generally less memory intensive than other scripting languages. This is because shells like Bash are designed to be lightweight and to execute commands and scripts quickly, in part thanks to built-in commands. In this lecture, we are going to learn command types and how to know if a command is a built-in command, built-in commands and its performance benefits. Fixing the chef analogy we used previously, we can say that the chef is like a parent shell that is able to spawn other processes and keep track of their tasks. If the chef could only manage tasks and resources by giving orders and asking other people to take care of things, everything he did would create an overhead. Gladly, the chef himself has the tools and skills to complete some of the tasks he manages without having to spawn a new process. Things like chopping vegetables or preparing some dishes are things the chef can get done himself without occupying a new resource. So in this analogy, built-in commands are like certain tasks the chef can get done himself without occupying more resources. Built-in commands are programs that come prepackaged in the shell that don't generate an additional process ID to run. This has significant implications in terms of performance, as built-in commands execute faster than programs we execute through binaries. We are going to categorize the commands we use in the command line in two main different categories. Programs with binaries. Some commands we use, like ls, have a binary that can be found somewhere in our file system. When we type ls, for example, we are executing the ls program through its compiled binary file. Built-in commands, commands that come prepackaged in the shell that don't generate additional process IDs when executed, like the echo command. To determine if a command is a binary or a built-in command, let's use the type command, which is a built-in command as well. If we use type against the echo command, we get that echo is a shell built-in, whereas a command like cat shows where the executable is located. In this case, it's usr bin cat. So cat command is not a shell built-in command. Instead, in this sample, cat has an executable binary in usr bin that can be executed and which will generate a process ID on invocation. Next, we will use the time command and the true built-in command to compare how much faster is a built-in command when compared to an executable binary. True is a command that returns successful status used in scripts for conditional checks. Time measures the execution time of a specified command in shell, displaying statistics for that particular command's elapsed real time, CPU time, and system time. If we type the command's time and true, we get that the command took 0 seconds and 0 milliseconds to execute. However, if we instead use the path for the true binary located in usr bin true by typing time usr bin true, we can see a slight difference in performance. With time true, the command takes 0 seconds and 0 milliseconds to execute. usr bin true and true are the same program. The difference is that when making reference to the absolute path of usr bin true, we're referencing the compiled binary, and when we simply use true, we reference the shell built-in counterpart. Both perform the same function, but they're executed differently. In this case, we see how executing the absolute path of usr bin true takes us slightly more time than true, demonstrating how built-in commands are more resource efficient. Now, to demonstrate how a built-in command doesn't generate a process ID when invoked, I'm going to use the trace command along with the exec system call to see the difference. To run a trace command to trace the system calls made by my current shell session, I need to get the process ID from my current shell, for which I'll use a pgrep-o bash command. See how pgrep-o returns an integer number. This is the process ID from my current shell session. I can do ps-ef pipe-grep bash to list all running processes and filter those with bash in their name to visualize how the ps command, which displays process information in Unix, is returning the same PID. I'll use pgrep-o to save me the trouble of parsing the ps-f output to get the process ID. Now I'm going to run a trace command by expanding the process ID using a command substitution expansion to access the process ID value returned by pgrep-o. This will help me trace all the system calls associated with my current shell session. Additionally, I'm going to grep for exec to filter only the system calls associated with running a process. Observe how when running an echo hello, we can't see the exec system call. But when we execute cat to file.txt, there's a process ID associated with this call. This confirms that built-in commands are both faster in execution, and also that they don't generate an additional process ID. This performance difference might not seem as much, but consider how much shell built-in commands can help with performance, where a large shell script with hundreds of lines gets executed, on where each of the commands would be generating a small latency if executed as binaries. Now let me clarify something I think might confuse a few people when studying this topic. Built-in commands also have binaries that can be found in our file system that we can use to execute the programs. We just saw that echo is a shell built-in command, but observe how using the which command, which reveals the absolute path of an executable binary, produces an output with the location of an echo binary somewhere in our file system. In this sample, I get that echo's path is bin/echo. If we use the type command against the absolute path of the echo binary, we get type bin echo as bin echo. This means that type is revealing that this echo sitting as a binary on the usr bin directory is an executable binary. If we use again type against the word echo with no absolute path, we see that it's in fact a shell built in. To compare the execution speed between echo and its binary counterpart in usr bin, we're going to use the time command against both. Here, we see how the usr bin echo, which is the binary executable, takes a little longer to execute when compared to plain echo. This confirms that the executable binary counterparts of the shell built-in commands are a different program than the one called by the parent shell on execution. Using the man command on either built-in or bash will give you a list of built-in commands available in your current shell. This, depending on the version of Linux you're using. Before we close this lecture, I want to talk about something very important. Throughout this lecture, we used the command time to measure how fast a command would be. Technically speaking, time is not a command, but a keyword. Keywords are special words that can be parsed by the shell to perform a certain action. While keywords don't generate a process ID either, keywords and built-in commands are not the same. Generally speaking, keywords are more closely related to control statements like loops and conditional statements. The time keyword is a rare case, as a similar functionality program used to be a shell built in some versions of Corn Shell, but in GNU shells like the modern Bash, it appears as a keyword. To see available built-in commands in your current shell, you can use the command compgen-b. To see the available keywords in your current shell, you can use compgen-k. We will explore more about built-in commands versus keywords in the next lecture. In our previous lecture, we discussed that the shell offers built-in commands in addition to the binary programs we typically use when interacting with the command line. One notable characteristic of built-in commands is that they do not generate a separate process ID when invoked. We also briefly mentioned another category of commands called keywords, which similarly do not create a process ID. In this lecture, we will delve into the differences between shell built-in commands and keywords. The key distinction between the two lies in their usage. Shell built-in commands are, in essence, programs that can be executed on the command line without generating a process ID. Conversely, keywords serve as instructions for control structures such as conditionals and loops conveyed through special characters or commands parsed by the shell interpreter. Using the same chef analogy we've been using to explain functions, process IDs, and built-in commands, we could say that executing a binary program like cat, grep, or find is akin to the chef delegating a task to a kitchen employee, which occupies a resource. Built-in commands are analogous to tasks the chef personally takes care of himself, which will help with the kitchen's performance. Shell keywords are special phrases used by the chef to dictate the repetition, order, or conditions for carrying out tasks. For example, the chef might say, "First, chop the vegetables, then start the grill. If the grill isn't ready, prepare 5 salads instead." In this analogy, shell built-ins represent the individual actions, such as chopping the vegetables, while shell keywords provide the framework for how many times and in what sequence these actions should be executed. We will now examine the case of two symbols, specifically the single square brackets and double square brackets, which represent a built-in command and a keyword, respectively. Here, we have an example of how both can be used in a script to evaluate conditional syntaxes and exhibit a similar behavior. In this case, evaluating the equality of two numbers, and if true, the statement inside the if block would be executed, otherwise ignored. However, since single square brackets and double square brackets are two different things, there are some important differences we can observe. We just established that the built-in commands are executables that can be directly typed in the command line, and they would generally have a binary counterpart somewhere in our file system as well. To support this claim, we can see how the single square bracket built-in command has an alternative way of being called, which is the test command. To verify that they are in fact the same program, in most versions of Bash you'll be able to see their man page by typing man test or man single square bracket, which will return an identical man page for both. This means that the single square bracket can be executed as a standalone command, directly in the terminal just like any other command, by using its test alternate name like in the example on the screen. This is a counterpart of the last test command, but using single square brackets instead. On the other hand, the double square brackets are symbols that the shell parses instead of executing them. Of course, the double square brackets can also be used directly in the command line, but there's no alternative command or binary for double square brackets, as there is for the single square brackets in the test command. I hope these comparisons will further clarify the nuances between built-in commands and keywords in the shell environment, so if you ever wonder if you should use single square brackets or double square brackets in your conditional statements when writing shell scripts using bash, you're in the right video. As mentioned, the difference is in the range of conditional expressions that each is able to evaluate. In this example, the single square bracket is taking the less than symbol as if it was a redirection symbol for passing input, instead of an actual less than symbol. Double square brackets, on the other hand, allows the less than symbol to be used as a conditional expression as seen on the sample presented on the lower half of the screen. This is because double square brackets are a more modern and feature-rich alternative to single square brackets, and you may want to use them in your shell scripts if your shell supports them. Here are some more differences. You can do grouping expressions using parentheses like in this sample using double square brackets. Double square brackets support pattern matching using both globs. In regular expressions, you can type all these commands directly on the terminal and you'll be able to see the output. So for these things alone, I think double square brackets are in my opinion worth using them when available. At this point it's pretty clear that I prefer using double square brackets. However, I think it's important we list both their advantages and disadvantages so you can make your own choice. Advantages of single square brackets. Single square brackets are more portable. Single square brackets are more widely supported across different shells. Disadvantages: a narrower selection of conditional evaluation syntaxes. Advantages of double square brackets: more support for pattern matching with strings. A wider selection of conditional evaluation syntaxes. Disadvantages: lack of backwards compatibility. They're not POSIX compliant. So after taking that little detour where we explored the differences between single and double square brackets specifically, let's have a more generalistic view between keywords and shell built-ins. They're both similar in the fact that neither generate a process ID. Their main difference is that shell built-in commands are programs, and keywords are special symbols or characters that are parsed by the shell interpreter, not executed. Keywords are generally associated to control structure, loops, or conditional evaluation syntaxes. This is true regardless of the corner cases. For example, time is a keyword, and it isn't used for control structures like other keywords generally are. But with the knowledge acquired in this lecture, we now understand that when using time instead of invoking a program, the shell interpreter will parse the token and do something.